Hello and most welcome to 1912 of our H series. We will today continue with the article Some Remarks on Wittgenstein's Philosophy of Mathematics by Richard Startup. Let's start the whole thing up. Last time we ventured into new areas, but also repetition. What we've learned before is quite usable still, or rather, it gets enforced. Now, when you put it in mathematics, why is that? Well, mathematics is closely linked to physics. The understanding stretches way into physics, and I'd say quantum mechanics. When we are finished with this paper, we will dip our interest into Feyerabend. Kalle Lundahl here was kind of me to remind that we are closing in on the centennial of Feyerabend's birth.
Hooray, hooray.
Hooray, 100 years. He wrote an article around 30 pages, 25, 30 pages that we can look at into. It will reinforce what we're going through here and what we learned when having a look at Paul Johnston, Francis Y. Lynn, Canfield, Edmund Dane, Paul Horridge, and many others. Mathematics is also a sort of doing, but it of course will be explained in a different way. Do look out here, sometimes law is used, that the grammatical rule is a law. To know that or to be aware of that could be quite helpful. So law could be used instead of grammatical rule or use. As indeed the axioms are doings, extended doings, rather long doings, but they are still doings, actions. Absolute and foremost. However true and destined they might be. And we continue on page 57 where we left off last time. So Wittgenstein's argument centers upon whether we would feel the lack of a particular irrational number such as pi as indicated earlier. However, it is quite inappropriate to speak as though n fills a gap, because a gap is a measurable interval.
Measurable interval.
Interval. Nevertheless, since an irrational number is defined as the limit of an infinite series of rational numbers, it follows directly, as indicated by Wittgenstein, one could supply an infinite decimal expansion which coincides with that of pi up to a specified point. A point!
Point.
A point! However, it would also be the case that presented with any such infinite decimal expansion, one could show its divergence from that of pi at some subsequent point. This could be done because, as indicated earlier, the expansion of pi is given by a formula, and hence its decimal expansion may be extended to any required degree. It may be worth adding that the digits in that expansion exhibit no pattern in a certain sense. They have a random character. Random.
Random. Random.
Hence, no clear sense may be given to the notion of law in respect of that decimal expansion. Yet the very fact that there are formula giving its value to any required number of decimal places identifies and secures its unique place with the decimal expansions of irrational numbers. Given that the real numbers are closed with respect to the rational operations, a further twist may be given to the argument. Suppose we take the infinite series which sums to the value of pi and simply delete the first term. Then the sum of the residual series would sum to an irrational number with a value different from that of pi. In addition, the deleted term as a rational number would give rise to a further decimal expansion. Suppose these two decimal expansions are now summed, then the resultant is the value of the decimal expansion of pi. Hence, if the latter decimal expansion were considered as absent, we would feel the lack of it because there would be a violation of the rule that the real numbers are closed under addition. Hence, it is the rule concerning closure under the rational operations that underlies the claim that the irrational numbers are complete. Complete.
Complete.
Complete. Particularly given Wittgenstein's sensitivity to applications, it may be wondered whether irrational numbers are of use outside mathematics. Doubts may be raised because it is impossible to determine by any physical operation whether a given length is rational or irrational. Irrational. What is true, though, is that from a physical point of view, the definition of a real number by a convergent series of rational numbers corresponds to the determination of the value of some observable quantity by a sequence of measurements of greater and greater accuracy. Therefore, as Courant and Robbins argue, the real advantage which the introduction of irrational numbers brings to the mathematical description of physical phenomena is that the description is enormously simplified by the free use of the limit concept, for which the number continuum is the basis.
Basis. Basis. Basis.
6 transfinite numbers and the excluded middle. Wittgenstein addresses issues concerning infinity and denumerability, which are probably more readily appreciated given a necessarily brief presentation of context. Now considering the infinite class of natural numbers, 1, 2, 3, 4, 5, 6, and so on, one can set up a one-to-one correspondence between these numbers and the series obtained by doubling each of them 2, 4, 6, 8, 10, 12, and so on. Following Cantor, one defines an infinite class as one which can, as in this case, be put into one-to-one correspondence with the part or proper subset of itself. In addition, if two infinite classes are such that a one-to-one correspondence can be set up between the numbers, then it is said that the two classes have the same transfinite number of members. Where a class has the same transfinite number as that of the natural numbers, one says that it is denumerable or countable. Cantor went on to establish some further surprising results. He showed by a constructive and systematic method that the class of all positive rational numbers is countable. On the other hand, by an indirect method and using a diagonal process, he showed that the class of all real numbers between 1 and 0 is not denumerable. This leads on to the assertion that the transfinite number of the latter class is greater than that class of natural numbers. Numbers. Importantly, for the present purposes, Cantor's indirect method is a proof by reduction ad absurdum. That is, it proceeds by assuming the contrary and then showing that this leads to a contradiction. The school of intuitionists does not accept proofs of that type, and Wittgenstein is far from being impressed by it. And now we come to the point. Importantly, philosophy may in no way interfere with the actual use of language. It can, in the end, only describe it. It leaves everything as it is. It also leaves mathematics as it is. It leaves mathematics as it is. Yet in challenging the terms in which mathematical results are formulated, he sometimes seems to challenge the results themselves. Yet, in challenging the terms in which mathematical results are formulated, he sometimes seems to challenge the results themselves. Queries whether the relation n equals 2n can be used to correlate the set of natural numbers with one of its own proper subsets in the way just indicated. Again, he writes, one pretends to compare the set of real numbers in magnitude with that of cardinal numbers. I believe and hope that the future generation will laugh at this hocus pocus. Hocus pocus. Those, such as Wittgenstein, who object to the type of non-constructive reasoning employed by Cantor, focus inter alia on its character as an essentially indirect proof. As above, the form of an indirect proof follows this pattern. To establish the truth of a statement, one makes the provisional assumption that its contrary is true. Then by chain of reasoning, one produces a contradiction to the contrary statement, thus demonstrating its absurdity. Then, on the basis of the logical principle of the excluded middle, the absurdity of the contrary statement is taken to establish the truth of the original statement. Now Wittgenstein is conscious of ways in which mathematicians may import conceptual confusion into that discipline. For instance, as Moore puts it, by their unthinking commitment to the law of the excluded middle. Another symptom of an unwarranted realism. Importantly, one must note that in mathematics, there are examples where an indirect proof can be converted into a direct proof. But there are also theorems, such as Cantor's as given earlier on real numbers, for which the direct constructive proofs could not possibly be given, even in principle. There's little doubt that the complete banishment from mathematics of non-constructive proofs would constrict the growth of the subject. Wittgenstein is particularly helpful when directing critical attention to Cantor's claim that the transfinite cardinals constitute an extension of the concept of number. As Shanker notes, this phrase may be interpreted in either of two ways: an extension of the number concept in itself, an extension of the domain of the natural numbers. As Shanker notes, this phrase may be interpreted in either of two ways: an extension of the number concept in itself, an extension of the domain of the natural numbers. Wittgenstein would find the first claim acceptable, since he viewed number as a family resemblance concept. The second interpretation is much more dubious. While in conventional terms, there's a sense to the notion that the domain of natural numbers may be extended into that of positive and negative integers, and on into the real numbers, the notion that transfinite numbers derive from a similar extension is untenable. In the former case, the extensions are all to do with preserving and extending the use of the rational operations. But in the latter case, there is no such preservation of operations. Just about the only operations which are specified for Cantor's transfinite numbers are equal to and greater than, and the latter hardly works in the same manner as 2 is more than 1. You cannot multiply or divide with them.
Divide.
Unite with them or divide with them at all.
Divide and rule.
As already noted, for Wittgenstein, suitable application is the hallmark of meaningful mathematical activity. This particular arrow could be targeted on transfinite mathematics, which has virtually no use in non-mathematical context. Nevertheless, as Moore points out, one may ask such questions as, why need the application be external to mathematics? Why may not the development of its application lie in the future? As complex numbers found application in alternating current theory of electricity. Even lacking application, might it not usefully systemize other parts of mathematics? One must be sure never to underrate the complexity of both the internal and external connections of branches of mathematics. Seven, rules within arithmetic and geometry. The contrast with empirical propositions is again foregrounded in Wittgenstein's middle period writings. Motivated by an analogy with those propositions, people are inclined to ask, what are mathematical propositions about? But against this tendency, Wittgenstein forwards the suggestion that arithmetical propositions or pseudo propositions are not about numbers, nor are geometric propositions about geometrical figures. According to him, we would do well to direct our attention away from what they are about and towards the use which we make of them. Furthermore, in a key point which Ambrose draws from his work, where we allow nothing to count against a proposition, the expression for the proposition is being assigned a special role in the language, as a rule for the application of certain words. This may be illustrated by our orientation in the familiar type of tiling situation. Suppose one multiplies 13 by 12 to find out the number of unit squares needed to exactly cover a rectangle 13 units long by 12 units wide. Were one to find, upon counting, that the number of tiles needed is other than 156, the result obtained by multiplication according to the rules, one could conceivably respond in two different ways. Were one to say 13 times 12 equals 156 is false, one would be treating it as a proposition testable by experience. On the other hand, were one to say that the multiplication is correct, regardless of the number of unit squares counted, one would be using it as a criterion as to the correctness of the count, and hence independent of experience. The second is our established common linguistic practice.
Common linguistic
Practice.
practice.
As Ambrose explains, Wittgenstein's account helpfully bears upon the familiar puzzle that people sometimes seem to discover a fact of experience which they then go on to prove must be so. This would seem to give a matter of fact an a priori demonstration. The assertion that there are only 5 regular polyhedra would be a case in point. This proposition was believed centuries before it was actually proved. However, according to Wittgenstein, what is happening is that an empirical proposition arising out of experience is converted into a proposition which no experience would lead us to give up, which is quite grave. No criterion whatsoever. As Ambrose puts it, arithmetical propositions, though independent of experience, are in two ways dependent upon experience. In being suggested by experience and in having their special function rest on common linguistic habits. Furthermore, consideration of the relation between mathematical proof and experience rather dramatizes Wittgenstein's conception of mathematical proofs as Paradigms. Paradigms. Paradigms.
Paradigms. Paradigms. Paradigms. Sweet paradigm. Sweet paradigm.
There would, however, seem to be a significant difference between arithmetic and pure geometry in relevant respects. In the latter case, but not in the former, there's a discernible tendency of linguistic practice to assert that something is true of ideal elements, such as geometrical lines and circles. It is implied that it may not precisely be the case, for instance, for lines or circles drawn on paper. How true. On paper. Thus, in pure geometry, the proposition treated as independent of experience is that contained within the abstracted axiomatic system. Pure geometry proceeds against the background of continued understanding that there is a gulf between the world of experience and the abstracted model, even given the illumination that each provides of the other. It is that understanding which even eventually opens the way to the substantive question as to whether Euclidean or non-Euclidean mathematics or geometry is to be preferred as a description of the geometry of the physical world. Wittgenstein was fascinated by proofs of impossibility. For instance, those directed at problems in ancient Greek geometry concerning the straight edge and compass, trisection of an angle, squaring of the circle, and construction of a regular heptagon.
Heptagon.
Heptagon! Let's have us a heptagon.
Smells tasty.
It is tasty. It contains cheese. In the last 2 centuries, the impossibility of each of these constructions has been demonstrated by algebraic methods. However, within the framework of geometrical straight edge and compass construction itself, no such demonstration of impossibility could be provided. It is only within a radically different algebraic setting that the problem can be properly posed and solved. Wittgenstein is firm on the point that it makes no sense to talk of the non-existence of a construction has been demonstrated by algebraic methods. Modern algebra and algebraic geometry provide a new grammatical system and associated rules within which questions unintelligible within the system of ancient Greek geometry acquire meaning and become soluble.
Soluble.